Alright, we're looking now at sketching lines, circles and ellipses in the complex plane. Let's first of all look at lines. Now we're familiar with the representation of x equals a. Okay, x equals a. Okay, as a vertical line passing through the point A0 on the Cartesian plane. So, for example, we have y and x, our Cartesian plane, and x equals 2 will just be a vertical line, okay, parallel to the y-axis, passing through this point 2, 0 on the x-axis. Alright, in a similar way, y equals -3 would be a horizontal line parallel to the x-axis, passing through 0, -3. In a similar way, okay, an expression that looks like this, so z, the complex number being defined by Re of z equals a, where a is a real number. It defines the set of points whose real part is a. It is represented on the complex plane by a vertical line passing through point a plus 0i. So our example here, sketching the graph of z, which is the real part of z, which equals 7/2. It just represents a line which is parallel to the imaginary axis, because it's just saying it's a set of complex numbers whose real part is 7/2. Whatever the imaginary part is, that's irrelevant. The imaginary part is 7/2 in this. So Re of z equals 7/2 is a vertical line passing through 7/2 on the real axis. Im of z, which is the imaginary part of z equaling b, it's going to be a horizontal line. So in this one, this is a set of points whose imaginary part is -2, and so it passes through -2 on the imaginary axis and is horizontal, so it's all those values, sets of numbers. Okay, there are other types of lines generated on the complex plane using argz. Okay, so this is just your vertical and horizontal lines, but there are others. So argz, so strictly speaking, these are called rays, because they're not lines that extend infinitely in both directions as these do, so the arrows showing that it goes infinitely negative and infinitely positive, either vertically or horizontally. Rather, these rays start at the origin and extend out depending on the angle. This set of points here is the same as what we've got in this one, only translated -a units in the real direction and -b units in the imaginary direction. So let's look at these two examples. Sketch the following on separate argand diagrams. Z being the set of points whose argument is π/3. So remember, an argument of π/3 means that the angle will be formed from the origin at an angle of π/3 radians, and π/3 is going to shoot up at this angle, so we've got an arrow indicating it's going to continue up infinitely, okay, but it starts here at 0. So it could be a complex number that has any particular modulus, okay, so the length of the line might be any number of units, but the argument is π/3, and so this is just how we show that ray. This one here, argz plus 4 minus 2i equals π/3. The angle is the same, The only difference is that the starting point is translated 4 units to the left and 2 units up. Okay, so this starting point, so the actual, probably worthwhile noting that on that diagram is that we're going, our point here at which we've got our angle of pi on 3 radians. Okay, this point here is translated to the left 4 units and up 2 units. So the point is -4 plus 2i. That is our point here at which our line starts. It's not written on here, but it is worthwhile writing it on as -4 plus 2i as our starting point. So if you're required to draw this, okay, to sketch this set of points, then you'll need to make a note of that point, okay, and that's noted here. Now, you should note that there is an open circle here, because the very point there, obviously at the very beginning of the point, will not have a particular angle. It's only when you start to move out from that point will it have that angle, whether it's in this one or this one. Okay, so this open circle means that it's not part of the set, which is graphed. Okay, so now we're going to look at some circles. Now we need to understand that the absolute value of z is defined by the distance of a point from the origin on the complex plane. Okay, so well, when I say absolute value of z, it's really the modulus of z. But it works in the same way as any absolute value. So when we say the absolute value of 5, we mean what is the distance of 5 from 0? And it's 5. We might ask what is the absolute value of -5? We're really asking what is the distance of -5 from 0? Well, it's also 5 units. So that's where this idea of absolute value, changing everything to be positive, it's a scalar quantity. It's asking for a value, a distance rather than a particular direction. Okay, so our modulus of z is the distance of a point from the origin on the complex plane. So the set of points where the modulus is equal to r is going to be the set of points on the complex plane that are r units from the origin. Now, a set of points from the origin, okay, that are all going to be a certain distance will produce a circle. Okay, that is the definition of a circle. It is the locus, is what we say, LOCOS, the locus of all points from a centre, a particular central value. And here, this really is talking about the origin. Okay, so the absolute value of z, or the modulus of z, equaling 5, means that it's going to be a circle whose centre is 0, 0, and a radius of 5. If we had z being defined as this set of points here, which is the modulus of z plus a plus bi, being equal to r, works the same way as this previous one, except that it's going to be translated a units to the left and b units right, or negative a units in the real direction and negative b units in the imaginary direction. Okay, but it's still going to have a radius of r units. The centre will be negative a, negative b. Alright, so this particular set of points, so z being defined as the modulus of z plus 1, equaling 2, so our radius is going to be 2. We can see that already from that. This z plus 1 means that it's just going to be translated to the left 1 unit, and so our centre moves from 0, 0 to negative 1, 0. And this one, we can see that the radius is going to be 3 units, and the centre is going to be defined by this part here. Okay, so it's z minus 2 plus 3i, the modulus of that, and so it's being translated 2 units to the right and 3 units down. Okay, so its centre will be 2 minus 3i. Okay, so we just find the centre and we draw a circle based on this radius. With our work in methods in Cartesian form, a circle with a radius of r and a centre hk has the general equation x minus h squared plus y minus k in brackets squared equaling r squared. And so in the complex plane we can consider that as well. X being our real component, so that's the real part of z is x minus a, so instead of h we've got a, all squared, plus the imaginary part of z, which is y, minus b instead of k, equals r squared. So that's going to be a circle with a radius r and a centre of a, b. And so this is equivalent to z plus a plus bi, a modulus of z plus a plus bi equaling r. And you could work your way, you could work through that to prove that. What we'll do is we'll leave it at that for this video, and we'll pick up our work on ellipses in the next video.